Welcome to our deep dive into database design. Today, we're focusing on implementing many-to-many relationships in a database. A many-to-many, or MN relationship, is a common concept in entity relationship diagrams, but how is it translated into a physical database schema? Consider two entities, student and course. A student can enroll in multiple courses, and a course has many enrolled students. This is a many-to-many relationship. Crucially, a many-to-many relationship cannot be represented directly in a relational database. Instead, it requires an intermediary. To solve this, the MN relationship becomes a new, weak table, which connects the two related entities. This new table, let's call it student-course, logically sits between the original student and course entities. The student-course table must contain foreign keys. Specifically, two foreign keys are introduced, one referring to the primary key of the student table and another to the course table. Next, we define the primary key for this new weak table, which is vital for maintaining data integrity. The primary key of the student course table is a composite key made up of the two foreign keys, student ID and course ID. Using this composite primary key ensures that every combination of student ID and course ID is unique. This means a student cannot be enrolled in the same course twice. Beyond just structure, we need to consider data integrity rules and any descriptive attributes. Sometimes, the relationship itself has attributes, such as enrollment date. These are added as columns to the weak table. To maintain integrity, we often specify rules like on-delete cascade and on-update restrict on the foreign keys to manage how changes in the parent tables affect the weak table. Now let's look at the full implementation and how we name this weak table. The best practice for naming the weak table is to combine the names of the two related tables, like student course, with an optional qualifier, such as enrollment, for added clarity. This ISQL-create table statement shows the complete implementation, defining student ID and course ID as foreign keys, combining them into the primary key, and including the enrollment date attribute with appropriate integrity rules. The resulting schema effectively enforces the many-to-many relationship between students and courses through the intermediary student course table, ensuring a robust and flexible database. By using a weak table, we ensure clarity, uniqueness, and flexibility, making many-to-many relationships easy to manage in your database design.
Let us look into this participation activity of implementing many relationships. So we have an airline and we have a flight. And in between we have schedules. So each airline has many flights. So we have airline that has many flights. Occasionally, the same flight is associated with several partner airlines, right? Okay, so entities are implemented as tables. Primary keys are airline code and flight key. So entities are going to be implemented as tables, and the primary key will be airline code and flight code. Okay, so the many relationship becomes a new weak table. Foreign keys refer to the related tables. Okay. So the primary key is the composite of the foreign key. That is correct. Occasionally, the new table has additional columns. Air flight number is the number each airline assigns to a flight. Optionally, foreign key rules may appear on the diagram. So we have the rules to restrict or to escape. So as we go down, let's work on this participation activity just to understand deeper about many relationships. So a passenger may own several credit cards and a credit card may be shared by family members. That is true. So we have a passenger and a credit card, and who owns it? So the primary key of the passenger table is the passenger key. The primary key of the credit card table is the card number. So what are the foreign keys in the new table? Just as we did here, what are the foreign keys that appeared in the new table? Okay. So in this case, the foreign key will be the passenger key and the card number. The passenger key and the card number, those are the foreign keys. So if you chose card number, you can't be card number alone. The primary key of both related table become foreign keys in the new table. And the primary key of both related tables become foreign key in the new table. So you cannot rule out that there are no foreign keys because all relationships become one or more foreign key. So the correct answer is passenger key and card number. So what is the primary key of the new table? The primary key become passenger key and card number. That's true. So you can't say card number alone because card number is not unique in the new table since several family members can share a credit card. Primary key must be unique. So when you say the composite of passenger key, card number, and third column on the new table, the composite passenger key and card number is unique in new table. So no additional columns are needed in the primary key. So the answer still remains passenger key and card number. So what is the name of the new table? We call it passenger credit card. So the name of the table implementing a many relationship usually consists of the names of the related entities. So if needed for clarity, the relationship name may be inserted between the entity names. So in this case, it's passenger credit. So what if you say passenger credit card ownership? Okay. So when including the relationship names in the table is optional. However, if the relationship name is included, the name is usually inserted between the table names. Passenger owns credit card. So if you're including the relationship, then it needs to come in between. It should be inserted between the tables, right? So in this case, the correct answer is passenger credit card. Good. How did you fare on? Put in the comment section and remember to subscribe, please.